Okay, homework help for number 6. Let's get this one started. This is going to be a little tricky because I wanted to tilt my camera around for you guys, and yeah, I'm just having a hard time keeping things in the frame. So I'm actually going to be doing a little bit of manipulation here with an answer key that I have. All right, so number 1 is actually the same darn question, I think, as from website number 5. So, you know, you get one more shot at it and a little bit more practice. Okay, so let's just move on to number 2, and I'm going to reference you back to number 5 if you need more help than what you've already got here that you can see. All right, so for number 2, you're being asked about a disc. Let's slide this back a little bit. Okay, so we're being asked about a disc, and so what we're doing there with that disc, let's move this around a bit, shall I? So it's not distracting. All right, so the main things you're being told about this disc to start with, well, you should either look up or know the value of the inertia for a solid disc. You're given the mass, you're given a radius. The first thing you're given is an angular speed, and you're asked to find angular momentum when it passes through the center of mass. That's your softball question. That's your, you know, I omega. Now, part B, what is the angular momentum when the axis of rotation passes through a point midway between the center and the rim? That is prompting you to use the parallel axis theorem because you need the new moment of inertia. So, if that is something that you don't remember, let me jot it for you here. Let's see if we can see it. Nope. Put my hands right out of the way. All right, so you're going to use the inertia from the center of mass, which in this case is going to be 1/2 mr squared, plus the mass times the distance squared. And this distance, remember, is to the new axis of rotation. So once you do this calculation, you've got the new inertia, then you can find the angular momentum again, assuming that your velocity, your angular velocity, is the same. So that's not too bad. Now number 3 is a little bit tricky also. All right, so you are told that there's a particle and there's a meter stick, and yeah, so my work that I have from previous years is a little bit old, just so you know, but not too bad, I hope. All right, so we'll slide this on down. Okay, so you're given a 100 centimeter mark on a meter stick, you're given the mass of the meter stick, and you're given the angular speed. Now, the first thing you're given is a position on that meter stick, and you're asked to find the angular momentum of the system. Now, if you're not being given a position at either the 50 centimeter mark or at the 100, then there is no set formula. All right, if you are going through the 100, it's, I think, 1/3 ml squared. If it's through the 50, you're at 1/12 ml squared, and you can calculate it pretty fast. If otherwise, what you would want to consider is using the parallel axis theorem, which is what we've got right here again, but this is just for the meter stick. All right, keep in mind that there is also a blob on the end of the meter stick. You are going to need to find the angular momentum of the blob as well and add it on. Or actually, better yet, you can just do you can take the moment of inertia for the blob, which is going to be mr squared, add it on to the moment of inertia of the meter stick through whatever mark it's rotating through, then find the new angular momentum. Sorry guys, I'm tired. I'm yawning a little bit here. My apologies. Okay, part B is asking you to recalculate it with a new axis of rotation. That's not too tough to do either. Again, you're going to use the parallel axis theorem for the this is for the meter stick alone, and then you want to actually add on the particles' moment of inertia as well. If you have more than one object, you just add their moments of inertia together. So here's my parallel axis theorem over here. This is for the blob on the end, and then again, solve it for angular momentum after that. So I omega. That one shouldn't be too bad. Okay, number 4. Number 4 is a very straightforward calculation. You'll probably have more difficulty just trying to put the symbols in, without a doubt, because I know Allie came in and the system was just giving her such a hard time, which is too bad. But the math itself is really not that tough to do. Okay, so for part 1 here, you're being asked to, find the new angular velocity, and you've got one thing rotating, and then it's not, and then they're being combined together. So again, instead of adding up the masses, what we do is we add up the inertias. They're going to rotate with the same speed. That's the main thing. Be careful with the little symbols in the corner. Even though I know there's more than one way to algebraically express a fraction being multiplied by something, don't put the final or the initial, angular speed in the numerator. Put it out separately. I think you'll have better luck with WebAssign being fussy at you. Okay, now the same thing for the kinetic energy of the system is being all done in letters, but considering you have omega I and you should at this point have omega F, this should not be all that tricky. You know, the main thing to remember is that your inertias are being added together for the final rotational kinetic energy, and then they ask you to do a ratio. So again, you'll probably spend more time trying to format the darn thing than actually answering it. It's not that bad. Last one. You are being given, oh, look, it's our experiment, except you're not standing up. You're sitting down. Look at that. All right, so you're on the freely rotating stool with the weights. Notice they give you the moment of inertia for the guy in the stool altogether, and then there's the moment of inertia for each of the weights in his hand. So the main thing I want you to remember, again, is that you add that up. All right, if you have more than one object for the moment of inertia, then what you're going to want to do is add them together. Okay, so for me, when I did this problem back in the old bad days, right? There's my student and my stool. My masses, I'm going to have two of them, and they've got basically the same radius and the same mass. So then once I find the moment of inertia for those, I'm going to add it to the moment of inertia for this one and come up with a total. Okay, and then you'll be able to find the new angular speed using conservation, right? Inertia times omega equals inertia times omega. Find the kinetic energy of the rotating system before and afterward. Well, that's going to be dependent upon solving A, of course, because you're going to need to find, you're going to need to be able to use the initial angular velocity and the final angular velocity. But just a quick reminder that that is 1/2 I omega squared, not just I omega. Okay? So if you've got more questions, please make sure you pop in for help. I do have a department meeting probably till 8:15 because Mr. Zimmerman takes a while. And then I will be around to help you out. Okay? So hopefully this helps.